So I'm Darren Nattinger. I think most of you guys know me. I work in LabVIEW R&D. I've been at NI for over 20 years. A lot of you know me as the quick drop guy. I added quick drop to LabVIEW 11 years ago, and it's still going strong. In fact, most of the time, thank you.
You'll always be my scripting ninja.
Love you too, Alan. So most of the time I present, I'm talking about, making you a faster LabVIEW programmer, improving your efficiency. I talk about that so much people tend to get sick of it, actually, I think. If I'm honest, I sometimes see people roll their eyes when they see, oh great, he's gonna talk about quick drop again. I'm not talking about quick drop today. My presentation is called Quick Drop Your VI Execution Time. So today I'm going to be talking about how to improve the performance of your VIs, how to make your VIs run faster. Before I do that, as is my common practice, take a picture of that or write it down. All the slides and all the demos are at that location. In fact, if you don't want to hear my voice, you could probably just go out in the lobby and download all this stuff. Okay. But if you want to stick around and listen to what I have to say, or if you want to follow along my demos and go download the VIs, you can do that. It's all there already. So I've got this really detailed outline here. Why am I talking about this stuff? Stuff I'm not going to talk about, stuff I am going to talk about, and then real-world demos of the stuff I just talked about. Is that clear? All right, good. My outline was a success.
How many times have you used that outline?
I just came up with it. I'm going to use it a lot more though. All right, so why am I giving this presentation? I would estimate that about once a month, give or take, somebody comes to me and says, hey, I've got this VI that's running too slow. Can you speed it up? These VIs are coming from a number of applications. The DAC team has come to me. The LabVIEW performance team has come to me. Lots of people come to me with these slow VIs, but usually they're all, in a general sense, trying to do something with a large chunk of data. Doesn't really matter what the data is, but it's large and it's taking a long time. And over the years, I mean, if it's happening once a month, I'm seeing a lot of these things, and I noticed that I'm using a lot of the same techniques to speed these VIs up. A lot of the same tools, a lot of the same programming patterns on the diagram, so much so that I started writing them down, and after a little while I realized, oh crap, I could make a presentation out of this. So, everything I'm going to be talking about today are very simple, general purpose techniques for improving the execution time of your VIs. You guys probably know some of these. I'm hoping that there's some of these that you don't know, and that's what your takeaways can be from this presentation. All right. There's a lot of topics having to do with VI performance. These are the things I will not be talking about today. The trace tool is great. Show buffer allocations, that's the hide the dots that Brian was talking about yesterday. Profile buffer allocations is probably the coolest LabVIEW tool that you've never even heard of. Maybe some of you have. I'm not going to talk about how to benchmark your code. I gave a presentation a couple years ago called Brainless LabVIEW, and in that presentation I talked about good benchmarking techniques. I'm also not going to talk about how the LabVIEW compiler works, mainly because several of you in this room probably understand it better than I do. But there's a couple of links online that introduce a lot of concepts having to do with how the compiler works. You can go check those out. And I'm not an RT guy, I'm not an FPGA guy. Everything I'm talking about today has to do with LabVIEW programs running on the desktop. Here's the stuff I am going to talk about. I am going to spend quite a while talking about the VI profiler, the good, the bad, and the ugly about it. I'm going to be talking about the different execution settings you can make on your VI to improve performance, parallel for loops, programming patterns for making your VIs run more efficiently, and I have a little bit that I'm going to say about sets and maps. After you all suffer through the slides, I'm going to bring up some VIs and show you some actual VIs that people have asked me to speed up, and how I've used the techniques I talked about in the presentation to speed them up. All right, so I have a disclaimer here. There are some times where we have to do just silly things to speed up our VIs, okay? It's just like you see it and you're like, why did I have to do that to make my VI faster? If readability and maintainability is your #1 goal, which it almost always is, you're not going to do these things. But if you have written code that is readable and maintainable and it is too slow, you may end up having to do some of these silly things to your VIs to make them faster. I tried to delineate those silly things in my presentation with an exclamation mark. So when you see an exclamation mark, that's something that's like, oh crap, I really have to do that to speed up my VIs? Yes, you do. There's this famous quote from Ken Beck, make it work, make it right, make it fast. You always want to make it work, you usually want to make it right, and you only want to make it fast if you have to make it fast. And then Fabiola will probably add on, after you've done those 3 things, make sure it still works by running your unit tests that passed in the beginning of the whole thing. All right, so we ready? We're going to start talking about the VI profile. So its official name, because NI likes to give things names that are longer than they should be, is Profile, Performance, and Memory. But I've always called it the VI Profiler, and I know a lot of other people have called it that too. It's in the Tools menu, Tools Profile. This tool has been around forever. I managed to get a copy of LabVIEW 3 running on my desktop, and it had the profiler. I couldn't get LabVIEW 2.5 to run on my desktop, but maybe it has profile too, I don't know. So the profiler gives you information on how long your VIs take to run, and you can optionally have it give you information on the memory usage of your VIs as well. Here's how to use the profiler. It is super simple to use. You launch it, there's a little checkbox in the upper corner that says time and statistics, check that. Click start, there's normally a start button down there, but I took the screenshot while I was running, so it says stop instead. Then run your code, and after your code runs, click snapshot, and then start looking at the information to figure out how much time your VIs took. That's it. Very simple. In fact, that's the best thing about the profiler is it's low barrier to entry. Anybody can figure out how to use this thing to see how fast their VIs are running. The desktop trace tool is great. It is harder to get started using that thing than it is to use the profiler, which is why the profiler is my go-to tool for figuring out execution time. By default, the tool will sort your VIs by how long they took to run. You can sort by other columns, but I almost never do. I almost always just leave it with the default sort. If you have used the profiler for very long, like I have, you probably got accustomed to seeing VIs showing up in the list in multiples of 15.6 milliseconds. So you'd see a bunch that said 0, you'd see a bunch that said 15.6, you'd see a bunch that said 31.2, and it kept on going. In LabVIEW 2018, they improved the resolution of the profiler greatly, so you don't see those big jumps anymore. So if you remember seeing that, try using LabVIEW 2018 or later, you'll see that the resolution's a lot better. When you check the timing statistics checkbox, the reason that I check that is because I like to see the number of runs column over there, and that is useful for me to know if I should consider inlining VIs. If you have a VI that runs once, twice, 5 times, 10 times, 50 times, 100 times, inlining won't really help you out that much. When you have VIs that run thousands or millions of times while you're running your app, those are the ones you want to pay attention to inlining. The bad, this is a C-based feature. Oh, I have a question real quick.
Why can't you turn it on while your code's already running? You get bizarre numbers, and I have applications that run 24/7.
Sure.
I don't have the option of turning it on.
So the question is, why can't you run this thing while your code's already running? Once you start the profiler, there are hooks that are put into place into the execution system of LabVIEW that give us this data. Those hooks aren't normally there. So you have to run the tool in order to get the hooks into the execution system.
So does it actually slow down the execution?
It does slow it down, but usually not enough. When you're benchmarking VIs that are slow, the overhead of running the profiler isn't really a concern. You're probably not benchmarking VIs that are running fast enough.
It lets you run it, it just gives numbers that
Right, that's true. You can run this anytime you want. You'll typically get a dialog that pops up that says, hey, don't start using this while your VIs are running because you'll get bad results. If you click OK and then start profiling, you'll get bad results. So,
Oh, so it's a useful dialog.
a useful dialog. All right, so that's stuff about the profiler. A lot of the features I showed you guys yesterday that are in LabVIEW 2020 are G-based features, which means I can write them. The profiler is a C-based dialog, so I cannot currently extend the profiler. I gave this presentation as a run through to my team in LabVIEW R&D, and I could see the wheels turning where they were like, oh, maybe we could add some hooks to make this a G-based dialog. And I was like, yeah, let's get those wheels to continue turning. Another bad thing is that inline VIs don't show up. I'm going to talk more about inline VIs throughout the presentation. They're one of the easiest ways to improve performance. However, once you inline VIs, you will not see them in this dialog anymore, which makes sense. Like, as far as LabVIEW execution is concerned, that sub-VI doesn't exist because its diagram has been inlined into its color. But it's kind of annoying when you are interested in knowing how long they take to run.
So the caller's time will go up itself.
Yeah, so basically what that means is time that normally would have been assigned to a sub-VI, that time is assigned to the caller, and you don't see the sub-VI at all in the dialog. And then another bad thing about the profiler, there's a lot of distracting info here that if you don't know specifically what you're looking for can kind of get in your way. This is what you see. In my opinion, this is all you really need to see. You need to see the VIs, you need to see their times, and if you're interested in number of runs, you need to see that column. So again, this is where it'd be cool if I could extend this or run my own version in G, then I could have a nice streamlined looking profiler, but we're not there yet. So here's the ugly thing about the profiler. The time values that you see in the VI time column can often be unexpected compared to what you thought you would see there. You might have a VI that once you click the run button, if you had a stopwatch, and then once the VI stopped, you saw it took 10 seconds to run. If you add up all the numbers in the VI time column, you might see 10 seconds, you might see 5 seconds, you might see 20 seconds. It's really weird. But there's a few reasons why that's the case. One of the reasons is that if you have parallel operations in your VI, those get summed in the profiler window. So if you have parallel loops and you click the run arrow and that VI took 1 second, you might see 2 seconds in the profiler because we add up the execution time of those parallel loops. So that's kind of weird. Another reason is I learned the concept of LabVIEW friendly sleep time, which I'm sharing with you today. There are functions in LabVIEW that sleep. The wait function, obviously. Event structures, if you've got a TCP function, a TCP read with a timeout. Those functions all have what's called LabVIEW friendly sleep time, which means when you profile the VI, LabVIEW, in its attempt to be friendly, does not include that wait time in the total execution time of the VI, because obviously you're not benchmarking to learn about how long something waited. You're benchmarking to learn about how long something executed. As a result, you don't see those times in the profiler. But there is also unfriendly sleep time. For example, if you have a DLL call and your external code is sitting, waiting, sleeping, LabVIEW doesn't know that that's friendly sleep time. It just knows that's how long your DLL is taking to run. So as a result of those two different types of waits in your VIs, maybe sometimes the profiler won't count that time, maybe sometimes it will. So that's another reason why you can get unexpected times. So all this to say, I still love the profiler. It is my favorite profiling tool, but whenever you are using it, don't think of the times as being absolute metrics. Think of them as relative metrics. Focus on the big numbers. They may not be exact, but they're big. Watch those big numbers go down, and you know you're improving the execution time of your VI. All right, so the profiler also has checkboxes on the right for profiling memory usage. Why am I saying here to not use the profiler for memory usage? Well, early on when I said stuff I'm not going to talk about, I lied. I am going to talk about the profile buffer allocations tool, which is the best LabVIEW tool you've probably never heard of or never used. Whenever you are profiling for memory usage, the profiler, my favorite execution time profiling tool, gives you memory usage on a per VI basis. The profile buffer allocations tool gives you memory usage on a per node basis. So you can actually zero in on that bundle by name that is allocating a gigabyte of memory for the giant array of waveforms that you just passed into it. Whereas if you're just using profile performance and memory, you just know that this giant VI that somewhere on its diagram has a bundle by name allocating a gigabyte of memory. You know that VI is allocating a bunch of memory. This tool will very often allow you to zero in on the actual node. So again, this presentation is not about memory usage, but this tool is cool enough and a lot of people don't know enough about it. Tools, profile buffer allocations.
What year?
2016 SP1, I think. One of the few times we added a feature in SP1. I may be off by a year or so, but I specifically this was added in SP1. Oh wait, there is no such thing as 2016 SP1. So it must have been 2015 SP1 or 2017 SP1. Somewhere around there.
It wasn't 17.
It must have been 2015 SP1. Yeah, that's my guess, and I'm sticking to it. Okay. Yeah, what's up?
So right now I see the VI name and a thing, but the buffer ID number, and there's some way to link back to block.
Yeah, so again, I'm not talking about this, but I guess I am talking about this. When you double click on things in the results of profile buffer allocations, it will very often highlight a node for you.
Okay.
Sometimes it will tell you a compiler optimization made it so that I'm not sure what node it was, but a lot of the times it will tell you.
It's in 2015.
2015 SP1, thank you, John. All right, so here's the first exclamation mark of the presentation. This is a silly thing. Every time I show this to people, they're like, what, seriously, you do that? And I say, yes, and it helps. And they say, oh yeah, I guess that would help. So, oftentimes I have a VI diagram that is slow And I can't narrow the speed problem down any further than this diagram because it's all a bunch of built-in functions, or maybe there's a loop that's slow and like I'm not sure what part of that loop is slow. So what I start doing, and what I will demo later, is I start clicking various pieces of the diagram and doing edit, create, sub-VI. Just random sub-VIs and throwing in my code, which obviously I'm not doing to make changes to my source code. What I'm doing that for is so that I can launch the profiler and I can see those sub-VIs show up in the list. That allows me to narrow down performance issues on a more granular level than just a block diagram. It feels silly. Thankfully, we have undo. So once I figure out which part is slow, I Control-Z, 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 and all the sub-VIs go away, and I've got my diagram again. But this is a silly trick that I use to be able to narrow down performance issues when I can't go past the sub-VI boundary. All right. Hopefully that made the presentation worth it. Okay, so now I'm going to talk about VI settings. Just inline VIs that run a lot is your big takeaway from this presentation. The main reason, or the reason most people think of, is that it removes sub-VI call overhead. Another reason is that there's a lot of compiler optimizations that can be done across sub-VI boundaries, but there are a lot of compiler optimizations that cannot be done across sub-VI boundaries. When you inline your VIs, you've gotten rid of those sub-VI boundaries, so now you've got some compiler optimizations opened up to you. My colleagues in LabVIEW R&D say, don't mess with the priority settings, really. I mean, if you really know what you're doing and you really have a good idea, sure, you probably know more than I do, but inlining is going to solve the problems that those otherwise would solve most of the time. Derek, do you have something to say about this?
Well, I have a question. Is there a difference between inline share and inline reality?
Is there a difference between inline shared and inline pre-allocate? I don't think so.
No.
Thank you, Stephen. That's why I keep them around.
FPGA, right?
What's that?
It only makes a difference in FPGA. Because it is different how it gets filled into the FPGA code.
Fabiola is an FPGA expert, everybody. So she's the person to talk to about that. So another exclamation mark here. I have had to do this on a number of occasions, and I feel dirty every time I do it. But I'm trying to get performance, and so I do this. There are a lot of VIs that ship in VI-lib that are not set optimally in terms of their VI settings. There's a lot of VIs that should be marked as inline that are not marked as inline. There's some VIs that are not marked as reentrant that should be marked as reentrant. One example, I had to write a VI or an application that was doing some really intense picture control stuff. So there's a bunch of picture VIs in VI-lib, and none of them are marked as inline. And so I had to save my own copies of those VIs and mark them as inline to get better performance out of my picture control application. I've seen people do this and not change the icon of the VI. That should be a criminal offense. When you save a copy of a VI-lib VI, give it like a bright orange background or bright red or something. Make it really obvious that that is not the VI that NI is shipping. That is your own copy.
A big scroll crossbones on it or something.
That skull and crossbones, sure, but make it still recognizable though. You want to know what it's actually doing.
Throw it in the library and then apply the library icon on top of it.
That could work too. You could even use a text icon in LabVIEW 2020.
They're tall enough.
They're just the right height. Make sure you document the caller whenever you do this so that when you open the calling VI diagram, you'll see a comment that says, hey, this is a copy of this VI from VI-lib. I made it because I had to inline it. Okay, so again, inline VIs don't show up in the profiler, which is a bummer. So inlining is probably the last thing you're going to want to do after you are trying to get your performance down. Similarly, turning off debugging is a super easy way to improve performance as well. The number of times I've been sitting around in LabVIEW R&D and I've heard one of my colleagues refer to a compiler optimization, and then someone else would say, well, I have debugging turned off, right? And they'd be like, well, of course, because you don't get that compiler optimization when debugging is turned on. I've heard them say that so many times. So if you need more performance, one of the last things you should do, turn off debugging, if you're not making it in inline VI. Darren.
Does that matter runtime drivers?
It doesn't matter if you build EXE. I'm talking about, unless you built a debuggable EXE, I guess. But yeah, we're talking about stuff that's running in IDE. All right, let's talk about parallel for loops. Oh, but Jim has a question.
If you have a built PPL running in the IDE, it'll still benefit.
Right, if the VI, so yeah, basically the point is if you have a build output, but it still has a block diagram, whether it's a debuggable exe or a debuggable DPL. Turning off debugging still improves performance, but you probably, if you built it for debugging, you probably want to leave debugging on. All right, parallel for loops. Parallel for loops are the easiest way to speed up code if it has a block diagram that contains a for loop. It's the very first thing I look for when somebody gives me a slow VI. I look for for loops that I can parallelize. A lot of times in these applications that are dealing with big chunks of data, you've got nested for loops. The general rule is that you only want to parallelize the outermost one because there's overhead associated with setting up the parallel instances. So if you have nested for loops, then you're doing the overhead to set up the outside one, then you've got the nested for loop and you're doing overhead to set up parallel with that guy. And then the next iteration of the outside one, you're doing that overhead again. As a general rule, you only want to parallelize the outermost loop. However, there are rare exceptions, like in one of the demos I'm going to show you guys later, where a nested parallel loop actually does improve performance a little bit. So my guidance is set a for loop to parallel and see if your VI breaks. If your VI breaks, it can't be parallel. If your VI is still runnable, it could be parallel. So one thing about parallel for loops that I have always found confusing, maybe it's really obvious to you guys, but it never was to me, is what to do with that number. When you configure a parallel for loop, well, I happen to sit next to the guy who is the lead developer for parallel for loops, so I asked him, and there ended up being this big, long conversation, argument, I don't know what you want to call it, between him and me and other members of LabVIEW trying to figure out what the hell I should tell a room full of CLAs about that number. There was a point where somebody yelled out, just use 8 all the time, so I put that in the slide. I thought it was funny. The number you put in that dialog is absolutely the maximum number of parallel instances that LabVIEW will generate when it compiles that block diagram. So if you are on a 16-core machine, but that dialog says 8, you will never get more than 8 parallel instances of that for loop, no matter what you do, no matter what you wire to this P. I used to think that this was smart. I used to think that getting that CPU information primitive and wiring number of logical processors to P would always give me the number of instances on my computer right now. It does not. It does exactly the same thing as if you leave that unwired, which is LabVIEW decides how many instances to generate up to that number in that dialog. You will never have more instances generated than what you see in that dialog. The help is unclear on this. I have filed a bug report to the documentation team to make it more clear. So, if you listen to Steve in LabVIEW R&D, you will always use 8. If you are, if you know for a fact that you are deploying this code to a machine that has more cores, then set that number to whatever number of cores will be on that machine. Don't set it to 64, which is the maximum number on there, unless you're deploying to a 64-core machine, because it makes no sense to increase your code complexity to have 64 instances of this for loop when you're running it on a machine that only has 8 cores. Steven, you have something to say?
I just want to say there's some scientific numbers behind that 8. It's not just pulled out of thin air, and there's some serious real reasons why most parallel systems today use 8. That is a number that has to be reevaluated. The CPUs get faster, so in about 10 years, we'll probably come to that.
But for now, just use 8. But I happen to know somebody who works on an application that does this really intense image processing, and that machine, they know for a fact, has 12 cores, so they have set that number to 12. But you have to know that. Aaron, yes?
So would setting it to the maximum of 64, but then using the CPU information to decrease it, allow you to have more performance on machines that have more cores and effectively be self-adapting to?
At the expense of increasing your code complexity, yes. You typically don't want to have 64 parallel instances generated when you don't need them.
But using the CPU information in the lower left corner, wouldn't that automatically drop the code complexity?
Again, you never need to do this because it's exactly the same as this.
But wouldn't, I'm asking, wouldn't that, if my CPU, if I could set it to 64 and my CPU information says I only have 4 or I only have 8, wouldn't that drop the number of generated parallel loops?
Well, it's always going to generate 64.
Okay.
So does that P do anything?
The P does, so look at my little comment here. If you wire a -1, we use what's in the dialog. If you wire a 0, LabVIEW is going to use the most available logical processors up to the value you configured in the dialog. If you wire any other number, it's going to use that exact number up to the number configured in the dialog. You will never get more instances than what's in the dialog. Chris? Change what change? No, because what if you have that dialog set to 8, but you want to use 3 cores because you're Chileno and you do weird stuff?
I think that's what he was saying, though. He was saying that if you set it to 64 and then you wire
There are
the actual number of cores.
So the actual number of cores is what is used if you leave it unwired.
Here's the thing that cleared this up for me. If you have, let's say you have a pre-allocated reentry VI inside your parallel for loop. You have a pre-allocated reentry VI inside your for loop. When you set that number to 8, it creates 8 instances of that in your compiled code. And then if you had 4 CPUs in the code that happen to be running your code, you're only going to use 4. So when you set that number to 64, you are pre-allocating 64 versions of that reentry PI during compile time, and then you go and give that application out to stuff. So if you have a bunch of plus primitives in your parallel for loop, nobody cares. If you have legitimate big VIs that are pre-allocate and this, and you're doing complicated things, you could be very significantly increasing the complexity and memory footprint and all this kind of stuff of your code. That was what made it click for me.
Derek, I couldn't have said it better myself. Clearly I didn't because they needed to hear what you had to say. So, I'm going to keep moving. All right, let's talk about some patterns. Some of these are pretty simple. You guys probably know most of these. This first one's pretty brainless. Always put your control and indicator terminals on the top level block diagram. Steve Rogers in LabVIEW R&D, who has worked in NI since LabVIEW 1.0, asked me to make sure to include this because it is the simplest way to get the compiler to figure out some ways to optimize the execution of the VI. If it's a sub-VI, that means it's got controls and indicators coming into it. Make sure those are sitting on the top level diagram. If you can, remove decision points from your diagrams, do it. Get rid of that silly error case structure around the diagram, get rid of that. If you can get rid of select nodes, other case structures, there's always, the compiler always likes it when it doesn't hit a decision point. So unfortunately, this next one, the basic string primitives I have found are almost always faster than using XML primitives, JSON primitives. I have had applications, I'm going to show you guys one where I got a modest performance improvement by getting rid of JSON primitives and just using like match patterns. I mean, it feels silly. But again, if performance is your #1 goal, you have to do those silly things sometimes. Similarly, LabVIEW class accessors, if you can pull those out of tight loops, that's something I calls you don't have to make. Also, in one of my demos, I'm going to show you that getting data out of classes first so that the tight loop is only dealing with basic data types also is a way to improve performance. And again, these are things that you do once you've made it work and once you've made it right. If you have to make it fast, these are things that you can do. A few other things. In-place element structure, obviously. Now, when Brian was talking about the in-place element structure yesterday, I was sitting in the back and I was sitting near somebody and I heard somebody mumble, the in-place element structure is sometimes slower. And I thought, what? It is? Please send us a bug report if it is, because it shouldn't be. So whoever said that, try it out in 2019. Yeah, it's that guy right there. Send us a bug report if you could reproduce that in 2019, because we should never have an in-place element structure be slower than replace array element, bundle by name, etc. Another pattern that I've seen people do sometimes is they'll have the in-place element structure with the unbundle and the bundle. They won't even use the unbundle. They'll just bundle in the value on the right side. You don't need to do that. Use a bundle by name function. It's the same thing. You're making your diagram bigger for no reason. One thing you should never do, though, is take your array, delete stuff out of it and change it, and then rebuild that array. I'm telling a room full of CLAs this because I have seen CLAs do this, and it is super slow compared to a replace array subset, as you will see in one of my demos. And then, if you have a large array and its wires being branched, that's not necessarily a bad thing. There are things that you can do to a large array when branching its wire that won't make a copy. But sometimes a copy is made. You may need a DVR if you find that you're making copies of a big array in a bunch of places. It's usually the last resort. It's usually the last thing you want to do, because if you add on a DVR, now you're introducing a whole bunch of other possible problems with locking, deadlocking and stuff like that. So switch to DVR if you have to, but make sure you try other stuff first. All right, I'm going to talk about sets and maps. Now, everybody's heard good, better, best, right? Well, here's good, gooder, better, better, or best, and bester. So, a lot of the times you can get away with just using search one array when you're doing lookups. We have a malleable VI and VI-lib/array that lets you pass it a search algorithm, like a class or a VI reference, if you want to define your own way to search the unsorted array. But more performant is doing a binary search if you can. And for that, in 2019, we also added another malleable VI that lets you pass in your own class-based or VI reference-based search algorithm. But what has generally been considered the best way to do lookups in terms of efficiency is variant attributes. We've been using those for probably about a decade, maybe more. But in LabVIEW 2019, sets and maps were added, which is an actual real API for doing data storage and data lookups. The thing about maps that's great is that they eliminate the data type conversion that's required that you would otherwise need to do with variant attributes. With variant attributes, your key always has to be a string, and your data always has to be a variant. So that's just how variant attributes work. They're not even an API for data storage. It's just kind of a hack that we figured out that was a really efficient way to store data, right? Now, here's the thing about variant attributes. NI has recognized over the years how often they are used as a data storage mechanism and how much you guys rely on their performance. So NI has put a lot of effort into making variant attribute lookups very, very efficient. We've put so much effort into that it turns out that in some rare cases, variant attributes are actually the same or better performance than maps. It shouldn't be that way, but it is. But I will say that the times when it is the case are pretty rare. There's like a certain threshold of size of the array that's stored. I don't remember what it is. 5,000 elements. Are they faster with more or less? I forget.
Less.
So if you have, I hate having to say this. If you have a variant attribute lookup table where your keys are already strings, your types are already variants, and the size of the lookup array is less than 5,000 elements, you may find that variant attributes are just a smidge faster than maps. But most of the time, you're going to be in a situation where you're not and don't have those three conditions. So yes, Aaron.
Just a comment for those people interested in maps and sets that haven't used them previously. Do not use them in unpatched LabVIEW 2019. Download and install all the patches.
Which is good advice in general. Install the latest patches. So one of the things I've found myself doing is, I have LabVIEW 2019. I work with Steve, and I'm very well aware of sets and maps. But I still find myself, when I'm putting a VI together, just habitually adding the shift register with the array, with the build array and the case structure, and I'm having to retrain myself. If I'm dropping a search 1D array on my diagram, if I'm dropping a build array on my diagram, I actually have to stop and think, wait a minute, should I be using a set or a map here? So that's kind of what I'm asking you guys to do. Once you're in LabVIEW 2019 and later, start looking for places where you can use those. Question?
So let's say you have an array of like 10 to 20 elements. Let's say you have an array of 10 to 20 elements. Would search 1D array be equally as fast as sets or maps for very small array?
Right, so the question is, what if you have a small array? Should you just keep using search 1D array? Remember my presentation, I'm kind of focusing on like those times where you need to squeeze out the performance of your VIs. I guarantee those times are not when you have an array with 20 elements in it. So search 1D array is still fine there. All right, so it is time for me to switch over to my real world demos of all this stuff that I just talked about, unless I have another question, which I do.
Just a quick question. If you write code in 2019 using sets and maps, and you try to convert your code to an older version of LabVIEW, what happens?
So the question is, what if you do save for previous on 2019 VI with sets and maps? Same thing as with any VI that contains nodes that aren't in a previous version, you'll just get placeholder nodes in a broken VI. All right, so first real world demo. This is a VI that is taking a bunch of data that has been pulled from a TDMS file, and it is converting it into a comma-separated value text file. This is a VI that I got from the DAC team here at Anai, and they were concerned about how long this VI took to run. This VI is using a very small TDMS file. They had a folder full of gigantic TDMS files, and they were finding that this tool took like half an hour to run on that big folder. I've just got a small TDMS file here, so it takes a second. But looking at this diagram, a few things jump out at me. We've got this array of strings that we're building up, and then we were immediately passing it into another for loop to do stuff with. It seems like maybe we can combine those for loops. That's the first thing I thought of when I saw this. I wasn't sure about the performance of writing to the file. I honestly didn't know. Is that going to take up most of the time for the execution? Really didn't know. So what did I do? I launched the profiler. So I did profile performance in memory. I always check timing statistics, and I did start. Then I run the VI. Then I click snapshot. And I find out that this sub VI is actually taking most of the time. Now this sub VI is from VI lib, so that's a concern. And it's actually pretty simple. It's just making strings out of stuff in a timestamp. So I'm going to put that aside for now because I've got stuff narrowed down to one sub VI, but I noticed that the remaining time is this whole VI itself. So all of the stuff on that VI diagram that's not the sub VI is taking 600 milliseconds to run. So this is where I use my silly trick and I decide, well, let me make some sub VIs. There's one, and here's one, and here's another one. So now I can narrow down the problem a little bit. So now I can stop and I can do a start. And now you'll see the sub VIs are showing up in the list. Let me run the VI again. And let me go do a snapshot. And now we can see, so untitled 5, that was this VI right here. So it turns out the file I/O is not contributing at all to the performance issue here. So my first guess was kind of off. And untitled 6, which is this VI right here, wasn't contributing that much. So that's how we're generating the comma separated value. So most of our execution time is taking place in here. So we know how much time this sub VI is taking because we can see that here. And then we know an additional 400 milliseconds is this other stuff that's on the diagram as well. So if we close that down and get, oh, well, first, let me go do undo, undo, undo. So now my code's back to normal. Then get rid of some of these sub VIs just to clean up the panel a little bit. Now let me open up the VI that includes my performance improvements. You can see that it runs over 2 times faster, so that's pretty cool. And I got 80% of my speed improvement on this VI by consolidating loops. Like I observed pretty early on, it didn't really make sense for there to be 2 loops. Setting things to parallel, so you can see now that for loop is parallelized, and setting sub VIs to inline. So if I were to run the profiler right now, we actually wouldn't see any sub VIs show up because I've already marked it as inline. And then I got a 20% improvement by simplifying how the timestamp is generated. So here's that VI lib VI, but I saved my own copy of it. And as you can see, you might remember there were 2 primitives that were generating the timestamp string. I got that down to 1. So I noticed though that before I turned on inlining, when I benchmarked everything, this sub VI right here, the one that's generating the timestamp string, still is taking most of the time for this entire application. So I thought, well, what if I replace that with just a really simple iteration count instead of the timestamp in the file? So now, instead of taking 0.6 seconds to run, the VI ends up running a lot faster and only takes 0.19 seconds to run. So the DAC team, I was like, hey, why don't you guys just store iteration counts in your spreadsheet? And they're like, no, we have to have timestamps. So I said, well, okay. So that is a suggestion for improving performance. See if you can get the requirements to change. Unfortunately, I don't. All right, so any questions on that demo before I move on to the next one? Yes, Damien.
I thought that the compiler actually did loop combining. I've run into bugs in older versions of LabVIEW because of that.
Oh,
so that's kind of weird that you would get that.
So Damien says, does the compiler do loop combining? I think it does sometimes.
Oh, it did.
There might be a reason why this one didn't.
Why do you still have 2 loops?
Why do I still have 2 loops? Oh, in this code? Because I can't parallelize the bottom one. I can't parallelize the writing to file. But the writing to file was very little time with the total execution time.
Yeah, I'm just curious, if you, instead of using the timestamp to format string or whatever,
yep.
If you just like convert it to the timestamp cluster and then use like your decimal to strings and all of those, because you're not parsing that timestamp specifier, I'm curious if you get better performance.
I didn't think to try that. That's a good thing to try. All right, I'm going to move on to the next real world demo. All right, so this is some code that I got from a team internal at National Instruments that I've simplified a little bit. They had an array of complex numbers, and that array of complex numbers corresponded to some indices into a table. So given a complex number, they wanted to pull out the right index so they could go look up some data or whatever. 10 minutes, thanks, Stephen. We're good. So this is how they were doing it. They had the array of complex numbers, and you can see over here, close my context out. You can see over here, they're just doing a search on the array, and based on the index, pulling out the right index value to look stuff up in the tree. Okay? So they ran this code, and it took this lookup time. And they had heard, hey, variant attributes are supposed to be faster lookups, right? So let's switch out and replace our search1D array code with variant attributes. So they did, and they ended up getting a VI that took a lot longer to run. And at that point, they threw up their hands and sent me an email. So I looked at the diagram and I noticed that this is how they were doing it. You can see they're building the lookup table over there on the left by taking the complex numbers, flattening the string, and using that as the lookup in the variant attribute table. Then over here, they're taking the complex number, flattening the string, and using that for the lookup. This is what I was talking about before. Flattening to string is a very expensive operation time-wise. So the actual lookup taking place in the variant attribute table, yeah, that's fast. But turning the number into a string so they can do the lookup is ridiculously slow. So slow that it slowed down their app 4x. So I told them, hey, there's this really cool thing called a map that is super fast and doesn't have that string conversion that you have to do. If we look at the block diagram, we'll see in the upper left, I'm building up my map with the key being the complex value and the value being the index that I need. And then over here, there's no flattening, there's no unflattening because maps let you use any data type for a key and any data type for a variant without having to convert to and from variant. So getting rid of that conversion ended up making the lookups, as you can see, not only way faster than the variant attribute, but also way faster than the linear search through the search1D array. Question?
This is probably a stupid question. Can you type fast as good instead of flatten? For the variant implementation?
I probably could have. I imagine it probably still would have been slow.
Still would have been slow, you think?
Yeah, a little bit. Can you typecast a complex to a string? Yeah? Yeah.
You do an array of complex, but
Oh, okay.
yeah.
Not sure.
You can't typecast a complex to a string, but you're gonna get some weird.
Yeah.
There.
All right. So that's question real quick.
You worked in 2019.
If I was not in 2019, I probably honestly would have stuck with the search1D array. Alternatively, I guess I could have replaced the data store that I have with strings instead of complex numbers, but this is the simplified version of that. The real version, they're doing other stuff with the complex numbers, so couldn't really do that. All right, last demo. This is a VI that is taking an array of classes and converting them into some table data that we're using to store like in a database or something like that. I'm going to start this VI running, and we're going to look at its block diagram while it runs. So the first thing that you can see that we're doing is, we have a for loop. We notice a for loop. We are pulling some class data out, doing some sorting, and then based on the sorted array of information, going into another for loop, and then generating some the strings that are going into our table. Now, usually when you have a for loop that maintains state, you can't parallelize it. So that's one concern because we see those feedback nodes there. So we need to worry about that. And then, but you can see we've got the class data that we stuck into a cluster and then we immediately pulled out of the cluster again. So we've got accessors here and accessors here. Remember I said that class accessors in tight loops can sometimes be a problem. And then if we scroll over, this was the big red flag for me. And this is what I mentioned in my presentation and what I felt I should share with the room, even though it seems obvious to me. That pattern that you see right there is really bad. Don't do that. They are taking an array, deleting, or it's a 2D array, deleting a 1D array out of it, messing with that 1D array, then rebuilding the array again. That is an awful pattern for performance. But for whatever reason, it's like the natural thing that some people, sort of fall into doing. So if we go back to the front panel, hey, it's finally done. Whoops, what did I click? It took 26 seconds to run. So I gave this VI the old DNAT treatment, and it comes down to 2 seconds. So if we look at the diagram, I added some comments about what ended up taking, first of all, this diagram's a bit more complex than before. A lot of times when you make changes for performance, you are going to get code that's not as intuitive as the code before. The biggest performance change was, you can see down here, there's no longer a delete and a re-add. There is a find the spot that I want to modify and use replace array subset on that. But a couple of other things that I did. You may remember in the previous VI, there was a non-parallel loop that was pulling stuff out of the class, then a non-parallel loop that was doing stuff to all the data based on state. That loop is still there, it's still not parallel. I added a comment reminding myself, hey, maybe if you need to come back and revisit this, we can see if we can add some logic. But we can't parallelize because of these guys. But I did take a lot of the code that was being done in that loop, moved it into this loop, and made this loop parallel. That really gave us a big performance benefit. But another thing that I did, which is really ugly and disgusting, is I got rid of the JSON primitives because I found they were slowing me down by another 5%. And I replaced them with all this silly match pattern stuff. I am not a regular expression guy. I never claimed to be. There's probably regular expressions that do this better than my match patterns, but they worked and they were faster than the JSON. But now this code is super fragile. If the JSON format ever changes, this code will totally break. But was it worth it to get the 5% increase? That depends on what the requirements were for the project. Maybe it was, maybe it wasn't. Those are the kind of things you have to pay attention to. But yeah, I got all the JSON stuff that was happening over in this loop, pulled it into this loop in the pre-processing loop that's parallel, replaced it with string primitives, got all the class accessing done over here. You can see we're not dealing with the class anywhere over here. So now the accessors don't have to run in this non-parallel loop. And that's how we got the better performance. But mainly it was looking out for this crazy pattern over here with the delete and the re-add and replacing that with the replace array subset. And then there was another part where I had to sort of learn this the hard way. You can replace, so I had a 2D array in this case where I needed to replace like a little piece of the array, not just a single element, but multiple elements. The replace array subset function allows me to replace at an index with a 2D array, but it doesn't allow me to replace with a 1D array, so I had to add that extra little build array function there. I had to learn that. I didn't know that that's how it behaved. But all this to say, I did everything I possibly could to get rid of those deletes and then those re-adds. Any questions on that? Question?
The access is slow because the property nodes, or
yeah, they're sub-VI calls.
Well, it's specifically in this case, it's because they've got error handling on them. If you can generate the data accessors without error handling, performance goes way better.
Right, that's a good point. Yeah, when you use the property node accessors, you have to have VIs that have error terminals on them. If you create accessors that don't have error terminals on them, then you've opened up a potential optimization there. Question?
Does the in-place element structure allow you to replace just a single piece in a 2D array?
So the question was, doesn't the the in-place element structure let you do what you see there? I couldn't get it to work. Maybe there's a way to do it that I couldn't figure out. I should have called Damien, it sounds like. All right, any other questions on this demo? All right.
I can't open it, so.
bit.ly/slow-VIs. Parallel loops, inline sub-VIs, run the profiler, code will be faster. Thanks, everybody.